Now, another thing that you can do with gas chromatography that you really can't do very easily with TLC is to actually quantify the amount of a substance that there is in a single peak. And the way you do that is by measuring the area of the peak. So if this is your chromatogram, what you actually get on this axis is really, it's a voltage in effect. It's how big a response the detector has. But depending on the type of detector you use, for lots of them, they basically sort of ping every time a molecule arrives. And it doesn't matter what kind of molecule it is. So if you count up the number of hits per second, you're counting up the number of molecules per second, and therefore, in effect, you're measuring the amount of a particular substance. So this is the detector signal coming up here. But the important thing is that not for all types of detectors, and there are various kinds, but for most kinds of detectors, the detector signal is proportional to the amount of substance, to the amount of, I suppose we would say well, let's say to the number of molecules. Molecules of whatever substance, it's just proportional to the number of molecules arriving in a given time. So it'll be the number of molecules per millisecond or whatever that the detector effectively is measuring. So that's what the detector signal tells you. Along here, as we know, we have retention time. And if you expand this axis so that instead of seeing sharp peaks, you actually see what those peaks look like, they have some kind of shape like this. And what you can do, because all this is registered on a computer, is you can relatively easily draw a baseline across there and measure the area of the peak. And the area of the peak is proportional to the total number of molecules contributing to that peak. Okay, so you measure the peak area. If all the peaks had the same width, that would also be proportional to the height of the peak, which would be easier to measure. But they don't, for complicated reasons that we won't get into. Peaks can vary somewhat in how wide they are, and therefore you could have quite a lot of molecules, but if they're spread over a wider peak, the height would be misleading. So you need to know that it's the peak area that's measured, and that's proportional to the total amount of the substance, or in principle it could be substance says, so we'll just put the S in brackets, but it's less likely to be a mixture of substances in gas chromatography because the resolution is better, but it still could be. So it's proportional to the total amount of substance or substances causing the peak. And what that means is that if you measure the same thing for this peak, its total area, if you find that this has, an area of 10 and, units, whatever area units you're measuring, and this has an area of 16 units or 18 units, then what you would say is that in the example you have 1.8 times as many moles of this as of that in your sample. Okay, so you can quantify the relative amounts of each substance just from the relative areas of the peaks. And of course, one thing you can do is to spike your sample that you're injecting with a known amount of a substance, so that instead of just then having the relative peaks, if this was a substance you deliberately put in a known amount of, you could say, right, this is 1 nanomole of this substance, and therefore there's 1.8 nanomoles of that substance. So this area thing is a very important way of quantifying the amounts of stuff in a mixture, which is not something you can do with TLC, at least not very easily. So that's an important extra thing. So remember to learn peak areas proportional to the amount of substance. So it's one thing to know, in this case, for example, that you've got 3 times as much substance A as substance B in your sample because that peak is 3 times bigger than this one. But of course, often what you'd really like to know is not just the relative amounts, but the actual amounts. How many moles of A and how many moles of B are there? And it is possible to obtain that information using the idea of calibration. Okay, so calibration is a very important idea, because what it means is that all the computer that records the spectrum can actually measure is the area. It obviously doesn't know anything about moles and stuff like that. But what you can do is to calibrate the machine by putting in a sample which contains a known amount of a substance, a known number of moles. And provided your detector gives exactly the same response to all substances, in other words, 1 mole of all substance, of any substance, would give exactly the same peak size. Provided that's the case, then if you calibrate it with one substance, you can therefore work out what the areas of all the peaks are. That will, for certain types of detector, be more or less true. If you want it to be absolutely rigorously true, you could calibrate it with the substance you're actually interested in and then get an even more precise thing. Okay, so what does calibration mean? Well, what it means is that you aim to produce a graph which has peak area as a function of moles of a substance. Alternatively, of course, if you always inject the same volume, the number of moles in that volume will be proportional to the concentration. So sometimes you see concentration along the bottom, but it amounts to the same thing so long as you always inject the same volume. And what you do is, before you run your mixture, you run a series of samples which just contain your calibration substance, but in different known amounts. So you could make a standard solution, for example, and you could then dilute it to various lower concentrations, which you know accurately because you've done accurate dilutions, and you just plot a graph of what the peak area is as a function of the moles of substance. And what you get out of that is what's called a calibration curve. Now, actually, most of the time you get a straight line which goes through the origin. So what you would get would be a bunch of points sort of, like this, and then you would just say, right, that looks like they're pretty much on a straight line through the origin, so you draw your line sort of like that, and that's your calibration line. So the idea then would be, let's put some numbers on this and say, it's a peak area of 1, 2, 3, 4, 5, going up like that. And then you would come to your experimental mixture. So remember, these may not be the same substances, it doesn't matter, provided you've got the right sort of detector, and you just measure. So let's say this has an area of 4.5 and this has an area of 1.5 units. And all you do is you say, right, if the area is 4.5, here's 4.5 on the calibration graph, you draw a line across here, and then you drop the line down, and you say that gives you the moles of substance A. Right, because substance A gives a peak with area 4.5, and you just read across here from 4.5 till it hits the line, drop it down, and that tells you the moles of substance A. And similarly, obviously, substance B has a smaller peak at 1.5, so you do the same thing, draw the line across, take that down, and that gives you the moles of B. If your points lay on a curve, then you'd fit a curve to it, but normally it's a linear response, so you get a straight line like that. So calibration is really important, because what it does is extends gas chromatography from being a qualitative technique which just tells you what you've got in a mixture, to a quantitative one which lets you accurately say how much there is in a mixture. The other really crucial question, apart from how much of each substance is there, is, well, what is each substance in a mixture? It's not really very useful to know that there's 3 times as much of substance B as there is of substance C or whatever, if you don't know what those substances are. So there are really 2 possible answers to that question. One is that just like the RF value in TLC, the retention time in gas chromatography is a reproducible thing, provided the conditions are exactly the same. So that means provided you use the same column with the same gas pressure at the same temperature, and everything is set up environmentally the same, then the retention time will be the same every time you run a sample through the column. And so if you're, for example, routinely analysing the same kind of sample, so if you're doing like quality control on your wine making process or whatever, then if you know that the peak that comes out at 27.4 minutes is this particular flavour component, you can monitor the amount of that in different samples and things like that. Or if you know that when the wine starts to go sour you get peaks at 54 minutes or whatever, then again you can look for those. But more generally, that's obviously not a very good way of analysing a substance if you've no idea what the substance could be. If a peak comes out at 23 minutes and you go to court and you say, right, well I'm sure this person had traces of heroin in their blood because they had a peak with a retention time of 23 minutes. They would say, yeah, but there could be loads of other substances with a peak of, with that same retention time. So there's no proof that was heroin. And, quite generally that's going to be the case, that retention time as a way of identifying a substance is only really useful when you've got a pretty good idea what the substance is likely to be. So in general, when you're trying to analyse complex mixtures, you want something more definitive to tell you what the substance is that you're actually detecting. And the absolutely standard way of doing that, the combined technology, which is possibly the single most important technique in analytical chemistry, is called GC-MS, which stands for gas chromatography mass spectrometry. And the way it works is basically, as the name suggests, that instead of just having a gas chromatograph, what you do is you stick on the end of it a mass spectrometer, so that you separate all the samples out in the column, but either instead of or as well as the detector, you basically just feed the components coming out into a mass spectrometer, and you record the mass spectrum of each separate component in the mixture as it comes through. And then in real life, what you normally do is, if you remember when we talked about both infrared and mass spectrometry, we said that one of the most common things that people do with them in everyday life is to use them as fingerprints of individual substances. So the pattern of fragment ions, for example, in a mass spectrum can be definitive proof that this is a particular substance. And that's what analytical chemists, forensic scientists and people like that routinely do. That they have complex mixtures, they separate them out in a gas chromatograph, and then they use a mass spectrometer to work out what each individual component is. And the thing about both these techniques is that they can work with very tiny amounts of substance, so they're very well suited to analytical methods like that, where you may not have access to a large amount of stuff. It may just be some trace that you're analysing. So you need to know about the existence of GC-MS, and just explain that you could use the mass spectrometer as a fingerprint method to identify individual substances, but also, of course, if you had, for example, made a new substance in a synthesis or extracted a new substance from some natural product, it might not be there in the database, but then the pattern of fragment ions and the molecular ion, of course giving you the MR, would give you some clues to begin to figure out maybe what the structure of that substance is. So it's a very, very powerful combination, and you just need to know of its existence. And of course it's a way that they can commonly bring mass spectrometry into exam questions.